This is lesson 6 of Wolfram language. So in this video we'll be talking about making tables. So what I have here is the local documentation of what a table is. So essentially we can use a table to build vectors, matrices, or other arrays, and it's a very useful function because it allows us to repeat the command a lot of times without having to hard code every single time. So the first thing we would want to do is generate a table. So table of 5, 10. So this is an example of the first line. So the table expression n generates a list of n copies of the expression. So we see that that this table has generated 10 copies of 5. So that's the most simple version. And another example is, this is one that I use a lot. So what this gives us is 1, 2, and 3. So what this is doing here is the table is giving us I, and I ranges from 1 to 3. So when I is 1, we get 1. When I is 2, we get 2, and when I is 3, we get 3. So if we do let's do I cubed, comma, I goes from, let's do 3 to 5. Then we see that when I is 3, we get 27. When I is 4, we get 64, and when I is 5, we get 125. So by writing a table, we don't have to type in 3 cubed, 4 cubed, and 5 cubed. It automatically generates it. So just one thing to note, we can also put a list here, and that would generate this list 10 times. So that's just a small detail that I wanted to pick up on. So just one thing to note is, in a table, if we have I from 3 to 5, it only denotes integer values. But we can take this and then put an increment of 0.5. So let's do 2. Let's just do I to see it. So here we see that I goes from 3. I checks for values of 3, 4, and 5. But since we put an increment, it checks 3, 3.5, 4, 4.5, and 5. So tables also work for functions. F is not defined, or let's just clear F. I'm not sure what it was at. So let's say n goes from 1 to 10. Then we get F1 through Fn, which is great. So that was a basic overview of tables. Let's see if I have anything more to go over. Yeah, so I think that is pretty much it. Oh, let's take this example. Okay, not sure what happened there, but okay, let's take this example. And what this is showing us is, we have, so if we delete the list plot, we'll get a table of primes of the first 50 primes. So it generates from I. So the first prime is 2, the second prime is 3, and then we go on to the 50th prime. Then we can take a list plot of that, which we will cover later in the lectures. So it is able to plot the 50th prime and So the x-axis here represents the I values. Then the y values here represent the actual prime numbers. Okay, so we will be covering only the odd number exercises in the Introduction to Wolfram Language book. So 6.1. So the question asks, make a list in which the number 1000 is repeated 5 times. So this problem would be a very similar problem to this problem. So we'd make a table of 1000, comma 5, and that gives us number that gives us 1000 5 times. So let's move on to 6.2. So make a number line plot of the first 20 squares. So this is a similar problem to this list plot, so we'll just type in a function. So the prime I, comma I goes from 1 to 20. So if we generate this, we get the first 20 primes. So because the problem wants us to make a number line plot, we can define this as primes, then take primes, and then we can generate a number line plot here. Oops, and sorry, this is 6.3. We're only doing the odd ones. Okay, so 6.5. Use a table to get the same result as range 10. So we covered range in the earlier lectures, and so first we can generate the range here, and this is a very similar form that we saw above of generating I from I1 to 3. So we can make a table of I goes from 1 to 10, so we get the same one. So we can define that as range, and we can define this as table, and we can check we can check if range equals table, and indeed it is true. So we're done with 6.5. Moving on to 6.7. Make a table of list of the digits for the first 10 primes. So let's take this problem step by step. So the first thing we have to do is generate the first 10 primes. So how we do that is, let's change it up with k to show that it works for any variable. So we generate the first 10 primes, then the list of the digits. To find the list of the digits, let's actually change it to 100 to make it a little more interesting. So to find the digits of a number, there's a function called integer digits. So it gives us the length of the integer n. So we can try that out with 2022, and we get, okay, is it the number of digits? I'm not sure if this is the right one. Okay. Okay, let's think. Is it digit count? Okay, so I know there is a function for that, but okay, so let's do it the hard way. So we do integer digits, and then it divide, and then we get a list of 20 and 22. So what we can do is we can take the integers, and then we can take the length of the integers, right? So that gives us 4. So we can alter this table a little bit by taking the integer digits of that prime number, and then we can find the length of it. Okay, so just to reiterate, this is very inefficient code because there is a function in Mathematica that automatically does this operation for us. But because I cannot find what it is, we have to do it by hand, and that is by splitting the prime number into integer digits and then finding the length of it. Okay, so that was 6.7, and it would also be great if you guys could find a function command that does this automatically. So 6.9, make a table of the first 20 squares. Okay. Let's just retype that. Okay. Okay, so 6.9, make a table of the first digit of the first 20 squares. So to tackle this problem, we first have to generate the first 20 squares. So start with u. U goes from 1 to 20. Oh, whoops, forgot a comma here. So it goes from 1 to 20, so it's 20, whoops, my bad. So we generated the first 20 squares. So there's many ways that we can attack this problem. So the first way is dividing each number by 100 and then taking only the integer part of that. Or another way is we can make it into a list and then select the first digit of the list. So because it will be something similar to integer digits. So let's do that. So let's take the integer digits of that square. So we split it into the list. Then we take the integer digits and then let's get the first one of that. So that generates the first digits, and we can actually verify this by taking a value of 10. So you get 1. If we get 9, it's 81. So, and then if we can get rid of this 1, we get 8, 1 as it's 81. And just to get the first one, we can use double bracket of 1 to get the first one, and that gives us 8. So that is it for number 9. And just to note, there are many ways of solving 6.9, and that wraps up this unit for tables.